In this tutorial, we're going to look at inference for matched data using MCNEMAR'S test. Now again, we're going to use the CHIS health disparities example, but we're not going to look at this random sample of 500 people anymore. We're actually going to switch up the data set instead. We're going to start with these 500 people, but then we're going to restrict to the population of those who are below poverty. Then we're going to go into the data set, take those below poverty, and then find a match for them who is above poverty. Because if you look in the data set, there's way more people who are above poverty than below poverty in our sample. So we take the below poverty folks and find a match who is above poverty, and we consider that to be, quote, a matched pair. So now we have this sort of matched data. And what do we use to match them? I take into account in this analysis urban versus rural location, race, and gender. So those are the only covariates that I use to match. You can incorporate more covariates to get a better match, but those are the covariates that we've matched on. So in order to analyze this new match data set, we're going to use the MCC command in Stata, which does MCNEMAR'S test for you. So in this tutorial, go ahead and open the CHIS_matched data set. So we're using a different data set. It's now the matched data set. Open up Stata and we'll get started. Using the data browser, I go ahead and take a look at this data set. You can see that there's only two variables in the data set. One variable is this Dr. 0, which is among those who are above the poverty level, whether they visited the doctor in the past 12 months, and among those who are below poverty level, whether they visited the doctor in the past 12 months. That's the Dr. 1. So one line in this data set corresponds to one matched pair. So let's just look at observation 1. For observation 1, they have a 1 for Dr. 0 and a 1 for Dr. 1. So this would mean that for the individual in the matched pair who was above the poverty line, they did go to the doctor. For the one below the poverty line, they also went to the doctor. Now, if we were to look at observation 3 instead, you would see that the individual who was above the poverty line did go to the doctor. The one who was below the poverty line did not go to the doctor. So that's the basic structure of this data set that we're going to use. And so you can see that it's paired, it's matched data. Now to analyze matched data, we go statistics, epidemiology and related, tables for epidemiologists, and then go all the way down to this matched case control studies. An important note here is this is unfortunate. In Stata, they call it matched case control studies, but MCNEMAR'S test, you don't have to have a case control study, and this MCNEMAR'S command will work even when you don't have a case control study. In our example, it's not a case control study because we matched individuals. We matched one individual who was below the poverty line with an individual above the poverty line. If it was a case control study, I would have taken, say, an individual who didn't go to the doctor and matched them with an individual who did go to the doctor. So there's a subtle difference here. It's not a case control study, but we can still use MCNEMAR'S. So I just plug in Dr. 0 into one cell, Dr. 1 into the other cell, and hit submit. So before conducting MCNEMAR'S test, let's think about this. What's our null hypothesis and what's our alternative hypothesis? So even though we're in this setting with matched data, etc., you still end up with the same null and alternative. It would be that there's no association between poverty and visiting the doctor in the past 12 months, and the alternative would be that there is an association. Now, I've stated my null and alternative a little bit broadly here, but given the way that I constructed this data set, in this example, we're not actually generalizing to the same population. In the previous tutorials, we looked at the hypothesis of no association between poverty and visiting the doctor among all California residents. There actually is a subtle difference when I've created this matched data set, because what I did is I took individuals with poverty equals 1 and using their age, gender, and location matched them to an individual with poverty equals 0. So it's still a test of no association between poverty and visiting the doctor in the last 12 months, but it's no longer a test for general California residents. Instead, it's a test that's generalizable to the population with covariate patterns similar to those below the poverty line. So now we're sort of generalizing this hypothesis test to the population of California who has this covariate pattern that exists in the poverty equals 1. So this is a subtle difference, and if it doesn't register for you right now, don't worry about it. It's essentially still a hypothesis test of no association, but we're just generalizing to a slightly different population. All right, so let's go ahead and conduct our hypothesis test. First of all, how many discordant pairs are there that are contributing to the test statistic? Remember, for MCNEMAR'S test, it's only these discordant pairs that actually contribute. So it's those for whom either, these guys, it would be both of them went to the doctor in the past 12 months, regardless of poverty status. In these pairs, neither of the paired individuals went to the doctor in the past 12 months. But these guys are the ones where they had discordant outcomes. So this cell that's 2, that means that there were 2 pairs for whom the individual above the poverty line didn't go to the doctor, but the one below did go to the doctor. Now these 15 guys right here, those are the ones who the person above the poverty line went to the doctor and below the poverty line did not go. So immediately we see that there are more pairs where the individual below the poverty line didn't go to the doctor versus the one who was above. So it's these 2 discordant pairs that we're going to use. We don't use the concordant pairs. And so we find that there's a total of 2 plus 15 equal to 17 discordant pairs. So think about that for a second. I started out with a sample of 500. I did all this fancy matching stuff. And now I'm only using 17 pairs, which means I'm only using 34 data points from that original random sample that I had. Another thing to point out here is we are dealing with a relatively small number of discordant pairs. Because of that, you'll see that in this MCC command, they give you actually a large sample up here and an exact probability calculation. So when you have a small number of discordant pairs, namely less than 20 discordant pairs, you need to be a little bit dubious about the normal approximation, and you should probably use the exact test that's based on the binomial distribution instead, and this test does not rely on large sample approximations. Okay, so first let's just go ahead and let's assume we were going to use the large sample assumptions. What would our test statistic be? We would say our test statistic is 9.94, and this guy would follow under the null hypothesis. It would follow a chi-squared distribution with 1 degree of freedom. And using that, we would find a p-value. Our large sample p-value is 0.0016. So that would be if we wanted to do a large sample procedure. In practice, you would really want to present this exact MCNEMAR'S significance probability because of the few number or the low number of discordant pairs in this example. The next thing we want to do is we want to look at the odds ratio. So we go down here and we see that we get an odds ratio of 7.5. This is an exact odds ratio, and you can see that it goes from about 1.7 all the way to 67.6. So it's very wide. And that's just due to the small sample sizes that are being used in this example. If we think back to when we used the whole sample of 500 individuals, when we were looking at the Pearson chi-squared test before, we saw that we had an odds ratio of 2.0 with a 95% confidence interval about 1.1 to 3.5. So those guys they're really kind of difficult to compare just because, number one, this generalizes to a slightly different population, and number two, the sample size is so small here that we get a ridiculously wide confidence interval. Okay, so we've conducted our hypothesis test, we got our odds ratio, we got our confidence interval. Now let's think back, and again, we want to kind of compare the MCNEMAR'S test to the Pearson chi-squared test. And think about the following question. So even though we've decreased the sample size and sort of changed the structure of the data set, was this matching? Was it a good idea? Do we gain power by matching? Which test is really providing stronger evidence that poverty impacts whether or not someone goes to the doctor each year? And these are some really thought-provoking questions that you need to think through very clearly when you're reporting the results of your analysis. We see that when we do the MCNEMAR'S test, we get a much more significant p-value. We get this really wide odds ratio, but it is bounded away from 0. So it seems like we do gain some power by matching. In the epidemiology portion of this course, you're going to learn more about matching and how it's really a very useful design tool for improving precision in studies. By comparing individuals who are similar with respect to a bunch of individual factors such as urban versus rural location, race, gender, age, etc., we're comparing people who are more similar, and we can exploit this correlation between those individuals to gain power in many situations when these factors that we match on are predictive of our outcome of interest.